So here we're going to return to those special triangles, relate them to our trig functions, and then see how we can use them to solve some right triangles. So what we want to do is, with these triangles, we really want to memorize these side lengths, or at least know how to bring them up again for when we get to the unit circle. So in last week's video, I went through the how to find these side lengths and even connected it a little bit to the unit circle. So we'll see some of that coming up again here. But these are good things to memorize. And then if you don't remember this, you can go back to last week's lecture and see how we found these side lengths. So something we did for these is we set the hypotenuse equal to 1 for both of these. Let's start with our 45 here. So this has two of the same angle lengths, which is 45 degrees, 45 degrees. And when these angles are the same, that means these two side lengths are the same as well. And what we did is, using the Pythagorean theorem, we found that these side lengths are going to be root 2 over 2. And we want to use these exact answers, meaning not a rounded decimal. So let's see how this applies to sine, cosine, and tangent. Now, in terms of 45 degrees, it doesn't matter which one we choose to be located at. We could either use that 45 degree, that one. It doesn't matter, since those side lengths are the same. So let's just go ahead and imagine that we're in this lower left-hand corner. So that's our location. Again, as a refresher, so sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. So that's SOHCAHTOA. So if we're at this 45 degree angle, opposite is going to be the root 2 over 2. The hypotenuse is going to be 1. So really I have this square root of 2 over 2 divided by 1, but when we divide by 1, it doesn't really do anything. So we're just going to have root 2 over 2. We do cosine, so that'll be taking the adjacent side length divided by the hypotenuse. So we're going to be seeing the same solution, that root 2 over 2. And tangent, we're going to take root 2 over 2 from opposite divided by root 2 over 2 from adjacent. So what that will look like is root 2 over 2 divided by root 2 over 2. But really we have this numerator and denominator that are exactly the same. So that's going to be equal to 1. So that's our 45 right triangle. We have those side lengths, and then we can see sine, cosine, tangent coming through as well. All right, let's look at our 30-60 right triangle. So 60 degrees is going to be this larger angle measurement here, and 30 degrees will be the smaller measurement. And we went through and found these side lengths. What I mentioned in the videos and how I kind of think of these side lengths is, I have memorized that one of the side lengths is half and one of the side lengths is root 3 over 2. I have that in my brain. It's just a matter of knowing which is the long side and which is the short side. So the 1/2 goes with the short side length, and the root 3 over 2 goes with the long side length. So it's just a matter of visualizing that. So this root 3 over 2 is going to be along here, and that's the long side. And then the 1/2 will be over here, which is the short side. There are other ways of memorizing this as well. I'm just going to present you with the little things that go through my head, since we do have some memorization pieces that we need to do. All right, so let's focus on the 30-degree angle first. So let's say we're here at 30 degrees, which makes the 1/2 opposite. Root 3 over 2 is going to be adjacent, and then we have a hypotenuse of 1. So sine is opposite, which is the 1/2, divided by 1, which is just 1/2. Cosine is adjacent, that root 3 over 2, divided by 1, which is just root 3 over 2. And then tangent, we're going to take opposite, which is 1/2, divided by adjacent, which is √3/2. So this is going to be a 1/2 over √3/2. And when we have complex numbers like this, we want to get rid of this idea of having a fraction within a fraction. So to do that, we multiply by the common denominator. So we have a common denominator of 2, so it's like I'm multiplying the numerator and denominator by 2, and that would give me 1 over √3. Now I'm going to go even one step further with this and rationalize the denominator. So let's get a quick review of rationalizing denominators, because that's going to come up. I'll show my work for a few of them as we get a refresher of that. So rationalizing denominators means we want to get rid of the radical that's showing up in the denominator. And what we're going to do is multiply the numerator and denominator by the same number. And what that number is going to be is it's going to be the radical that we're seeing. So I'm going to go square root of 3, square root of 3. So in the numerator, 1 times square root of 3 is square root of 3. In the denominator, what ends up happening is, you can think of this a few different ways, but we're basically squaring a square root, which undoes itself. So all we'll have left over is just 3. So either you can think of that coming from having the square root of 3 in parentheses squared and how that turns into 3, or you could think of this as when you take 2 square roots and multiply them, you multiply the insides. So that would give you square root of 9, which just simplifies down to 3. So whichever way you're used to thinking about it, but the punchline is that by doing this, we get rid of the radical because we're essentially squaring a square root. So I just want to rewrite this solution as square root of 3 over 3. We want to rationalize the denominator when we do these. All right, so all of that is dealing with our angle of 30 degrees. Now let's look at if we were at 60 degrees. So if we're at 60 degrees, that √3/2 is the opposite, 1/2 is adjacent, and 1's still the hypotenuse. So for sine, opposite is √3/2, and then divided by the hypotenuse of 1, but that'll just leave us with √3/2. And cosine, adjacent is 1/2, divided by the hypotenuse of 1, but that's just 1/2. And then tangent, we're going to take opposite divided by adjacent. So we're going to take √3/2 over 1/2. And you can think of this multiplication by 2 in the numerator denominator. Really, when they're the same, is that they just go away. So really, this is the square root of 3 divided by 1, which is just the square root of 3. Okay, so what this gives us are some exact values. That if I need to know what the sine of 30 degrees is, it is always 1/2. So these are numbers that we can draw on no matter the situation, because this triangle doesn't change. These sine, cosine, and, well, tangent as well are coming from this idea of hypotenuse of 1, because that's what's going to lead to our unit circle. So whenever you need to evaluate these numbers, it always stays the same. So let's look at some examples of solving right triangles. So here we have a 45, 45, 90, and I have this side length of 12 millimeters. And I'm going to go ahead and solve for this side length of x millimeters. What I want to do is I want to use exact values here. Since we know what happens at 45 degrees and 30 degrees and 60 degrees, we want exact numbers instead of using a calculator. So what I need to do is choose one of the angles. So let's say I'm down here at 45 degrees, which will make this opposite, and that's our hypotenuse. So I want to use the trig function that relates opposite and hypotenuse, which is going to be sine. So if I take sine of that 45 degree angle, that's going to make a ratio of our opposite side length, which is x, over our hypotenuse, which is 12. Now from there, what I can do is make a substitution for sine of 45 degrees, that evaluates to be exactly equal to root 2 over 2. So this numerical value can be completely replaced, this trig function can be completely replaced by this numerical value. So that's my next step here, is instead of sine of 45 degrees, we're evaluating that as root 2 over 2, and then equals x over 12. So the idea being that even though this triangle doesn't look exactly the same as this triangle, that's fine, because this is kind of our base form of our 45, 45, 90, and that gives us these function outputs. So what I was trying to emphasize before is that those outputs won't change as the triangle changes. So now with this, we want to solve for x. So what I'm going to do is multiply by 12 on both sides, which will give us, 12 divided by 2 is 6, root 2 equals x. And what we have here is an exact answer. So we know that x is equal to 6 root 2, and then they gave us units of millimeters. If we needed a decimal approximation, then we would just put that into the calculator. And then just keep in mind, if we needed to know this other missing side length with the 45, 45, 90, those would be exactly the same. So that would also be 6 root 2 millimeters. So let's see doing this with a 30-degree angle. So we're here at 30 degrees. I have the opposite side length. I also have I need to find the hypotenuse. I also need to find the adjacent side. So we're going to be doing 2 pieces of work here. So, all right, let's go ahead and find the hypotenuse. Doesn't really matter where you start. It'll all tie together in the end. So to find the hypotenuse, I'm going to use the opposite side and hypotenuse, which is our sine function, since I want that opposite over hypotenuse. So I'm going to take sine of 30 degrees, and the ratio we'll have is opposite, which is 4, over hypotenuse, which is y. And then we could move things around to solve for y at this point, but I think it's better to just make the substitution here. So sine of 30 degrees, what we found it to be equal to is exactly 1/2. So we're going to make that substitution. So instead of having sine of 30 degrees, we just get to replace that with this ratio of 1/2. And then we'll have 4 over y. Then we're going to solve. I'm going to go ahead and use cross multiplication here, just to show you this if it's been a while. So cross multiplication equals, you multiply across, so we'd have 1 times y on one side, and on the other side 2 times 4, which is 8. So we just found our value for y. Now to find x, now we have 2 side lengths and just 1 missing. So we can either use a pairing of adjacent and opposite, or we could use a pairing of hypotenuse and adjacent. Something I mentioned before, and as long as we have this 8 correct, doesn't really matter whether or not we do this, but something I do is I always go back to the printed number just in case I made a mistake there. I don't want to bring that mistake into this other calculation since they're pretty separate from each other. So I'm going to leave the hypotenuse alone and instead use opposite and adjacent, which is my tangent function. So tangent of 30 degrees is equal to opposite over adjacent, so that's going to be 4 over x. Now what I found up above here is tangent of 30 is that root 3 over 3. So I'm going to make that substitution. Root 3 over 3 is equal to 4 over x. And I'm going to go ahead with cross multiplication. And with that, we'll have x times the square root of 3 equals 12. Then I'm going to divide by the square root of 3. Now when I do this, I'm going to go ahead and throw in another step here of rationalizing the denominator, so that I'll have x equals 12 root 3 over root 3 times 3 is, I'm going to simplify to 3, and then I'm just going to simplify that 12 divided by 3, so x equals 4 root 3. So some extra pieces there with that radical and getting a rationalized denominator, but the idea being this is a much simpler form than 12 being divided by the square root of 3. So we kind of want to have any radicals up in the numerator. Now when you get to the end here, since we're dealing with right triangles, something you could do is check your answer by using the Pythagorean theorem. Let's go ahead and do that for this. So what we found is the hypotenuse. So the idea is 8 squared should be equal to 4 squared plus 4 root 3 squared. So 8 squared is 64, 4 squared is 16, plus, and then how this would simplify, so we'd have 4 squared, which is 16, times square root of 3 squared, which is just 3. So how this will simplify is 16 plus 16 times 3, which is 48. And what we'll see is that does balance out to 64 equals 64. So you can check your answer with these, having these exact forms. If at any point you have to use a rounded decimal, just know that that might throw the check off a little bit. But with these exact values, you should get it to balance out. All right, last one with kind of a more complicated right triangle. So we have this mixture of 45 and 30, and we want to find x, which it kind of show it by the location of it there. We want to find x. We also want to find y, which is this side length. But x is not extending all the way to the end. But what we're going to do is with this triangle with the 30 degrees, we don't have any side lengths, so we'd be pretty stuck without this piece. So we're going to do some kind of traveling here. We're going to solve for some pieces and end up over to this triangle. So what I want to do is I want to find this side length right here. I'm going to go ahead and give it a name. I'm just going to call it h, since it's the height of the triangle. So we want to solve for h. I'm here at 45 degrees. H is the opposite side length, and then 8 is the hypotenuse. So relating opposite and hypotenuse is going to come from sine. Now, sine of 45 degrees is equal to opposite, which we're calling h, over hypotenuse of 8. Now I'm going to make my substitution that sine of 45 degrees is the same thing as square root of 2 over 2 equals h over 8. I just need to multiply both sides by 8 so I can get h all alone. And we're going to get h equals 8 divided by 2 is 4 root 2. So we just found this side length over here of 4 root 2. So now we can move over to 30 degrees. If I'm at 30 degrees, let's see, h is going to be our opposite side length, x is adjacent, and y is the hypotenuse. So let's see, let's go ahead and find, oh, it doesn't matter which order we go in. Let's go ahead and find x, go alphabetically. So we're working with opposite and adjacent. So tangent of 30 degrees equals opposite of 4 root 2 over adjacent, which is our unknown x. Now, tangent of 30 degrees is that root 3 over 3 equals 4 root 2 over x. Then I'm going to do some cross multiplication. So x times the square root of 3 is equal to 3 times 4 root 2, which will be a 12 root 2. Then I'm going to divide both sides by the square root of 3. And again, I'm going to kind of combine that along with rationalizing the denominator. So we'll have x equals 12 stays the same. Square root of 3 times square root of 2, so those will combine with the root 2 times 3, which is 6, and in the denominator 3. 12 divided by 3 is 4, so this is a 4 root 6. All right, now solving for y. So again, I'm going to go and use that 4 root 2 again. So I'm going to use opposite and hypotenuse, which is sine. So sine of 30 degrees is equal to the opposite, 4 root 2, over the hypotenuse, which is y. Sine of 30 degrees is 1/2. I'm going to do my cross multiplication, and we'll have y equals 2 times 4 is 8, root 2. So there's x, there's y. All right, so that's how we can use these triangles as kind of a basic structure, get these sine, cosine, tangent values, which we're going to use these so much more when we get to our unit circle, and we'll be able to refer to them a little more quickly than like having to look back at these. I'll teach you some ways to memorize how sine of 30 is a half and things like that. But then that's how we can take those sine, cosine, tangent values and solve right triangles that have these similar angle measurements.